So this will be the last class. And then as I said last week, what I'll do today is I'll post either tonight or tomorrow. Your exam will be posted on Canvas. You will answer the questions and then submit it. As long as it's handed to me next Wednesday, you'll be good to go. I should state this. I've gotten some emails. I don't even know if it's any of you guys particularly, but it's worth me pointing out. With the pass-fail grade option, due to this whole insanity this semester, you do not have to make that decision until after you get your grade. So you don't need to worry right now about should you take a pass or a fail. What you should worry about is doing the work, and then after your grades are given to you by me and the school, then you can make that decision. So you actually get to see what your grade is before you decide whether you want to pass or fail. So hopefully that makes sense. If you have questions or need that clarified, reach out to me or your advisor or somebody else. I'll be putting a bunch of information on our Canvas page tonight. Well, actually, maybe not exactly tonight. If it's not tonight, it'll be tomorrow afternoon. With the final, what your grade, you should have a decent idea of what your grade is going into the final. A lot of you have emailed me, and again, I don't know if it's any of you. A lot of people are emailing me, did I turn in homework 3? I don't know. Honestly, I can't get into my office right now, and I have a bunch of assignments in the office. I am not worried about that, nor should you be. So if you think you turned homework 3 in, but you don't have a grade for it, do not worry about that. I will take care of it. Don't stress about homework 3. Hopefully that makes sense, or homework 2 or 4. Just worry about the stuff that we've been doing, since we sort of went rogue and we're now online. Hopefully that makes sense as well. Does anybody have a question at all? Feel free to chat or or yell out if you have something. I'll just drink my water. Okay, so what we wanted to do then is we will pick up where we left off. We just want to polish off this last topic, and then we'll be done. And then you'll have a final. And that's it. And hopefully everybody has a nice, safe summer. All right, so what did we do last time we met? Well, so what we've been studying is confidence intervals. For the mean. Okay, so let's remind ourselves of what the problem is. We want to understand how something's distributed. Well, the example we did last class was how long does some product sit on the shelf? If you run a store, if you're a particular store that sells something, or you're a warehouse that stores things, one thing you might be curious about is, okay, if I have a product, how long do I expect certain products to sit on the shelf before they're sold? Or maybe, we'd like to know the average body temperature of a group of people who live in a certain part of the world, or you name it. If there's something out there we'd like to understand, particularly the average of something, we'd like to know if, when we gather statistics about it, if they are, or what we can make of it, what sense can we make of these statistics. So one of the things that we do is we sort of have this idea of what's called a confidence interval for the mean. And essentially, in layman's terms, here's the idea. We know that out there in the world, you know, okay, let's go back to, you know, again, I always use this example. Say we want to know the average height of a 20-year-old on this planet. Well, we understand that there's no way in the heck we can go and find every single 20-year-old and measure their height to calculate the true mean. But theoretically, we could. Theoretically, we could somehow calculate the height of every 20-year-old, and then we could compute the average of that. So what we do is we say, okay, it's impossible to do that, or it's not in a cost-effective, or it's not a reasonable thing to do. So instead we say, let's sample all the 20-year-olds. Let's go out and collect a bunch of heights of a bunch of random 20-year-olds, and then let's compute that mean. And then, as we've pointed out to many times, we compute that mean. That the obvious question to ask is, well, is it inaccurate? Is it a good representation of this theoretical, what we call population mean? And one of the things we talked about last week was a way to measure our confidence that it was that our sort of sample mean was close, if you will, to what we call the population mean. So here's what we wrote down. This creature, so this was sort of the formula. It's not really a formula, it's what's called an inequality. If you want to write it compactly, one way we can do it is we write this. So this was what we called the 95% confidence interval. So we sort of tried to give you some sort of intuition or motivation where this magical number 1.96, where it came from. It's nice for you to know what all these numbers sort of mean. So let's point that out on the next page. So I'm going to write it down again just so we have it. So let's sort of annotate what these numbers, letters I should say, but they all represent numbers. So this right here, this is the true mean or population mean. X bar is our sample mean. And you'll remember we gave a name to this scary looking creature on the right-hand side. This guy we called the margin of error. Now, that 1.96 kind of seems strange, but we can remind you where it comes from. It comes from the area under the curve. So if we draw a picture, so if we have our sort of, let's use a different color here. I don't want an arrow. Get that stupid arrow off here. There we go. So we have our distribution of our means. So this is, we'll call this the mu. And remember, this distribution looks sort of normal. And we want to get 95% of sort of the area under the curve. So if we are to take, we know that that's symmetric. We draw a line. We are imagining that the shaded area now is 95%. So if there's 95%, what does that mean? What's the area? Well, 95% means 0.95 if you write it as a decimal value. And so that means what's left over, the areas that's not shaded under the curve, is still left to be figured out. So if you take, 1 minus 0.95, you're left with 0.05. Now, if you take half of that, because you have the left tail and the right tail, so if you divide, and you think about the symmetry, that means what's left over here, you have to have an area of 0.0025, and then over here you have an area of 0.0025. And the key observation is, if you think about how this curve is created, then the distance from the mean to this point is exactly 1 point, not exactly, I shouldn't say that, is given by this number. So this is that number. And then similarly, if you go over here, it's the same distance. So this was part of, we tried to sort of explain what we were doing with this yesterday, or not yesterday, last class. So if you're curious about where that 1.96 comes from, well, that's where it comes from. Now, there's really a name there, not a name, but there's a more sort of professional notation that's used with this. And we're going to write that down in a second. Before we do that, though, does anybody have a question? Comment? So I'm trying to give you a sort of a look behind the curtain on why we're doing this. I'm not going to pretend that this is easy to learn, but you can learn it. It just takes some time. Okay, so this next question is what's special about 95%? When I started this off on Monday, I think I had a stroke this morning. Maybe I did. I don't know what's happening. When I started this off last Thursday, I just posed the question, how confident are we in something? And then I used the number 95, and then a good rebuttal from you would be, why 95? Well, I could have said, well, I want to be 99% confident, or I want to be 90% confident. So the right answer to this is nothing. It's just that 95 sounds good. So what we do is that we can ask about other levels of confidence. Say 99 or 90. So again, there was nothing completely specific about 95. It was just arbitrary. So, okay, we say, well, how does this change then if we wanted to use a different, if we wanted to be a different level of confidence? Well, if we wanted to do a different level, we just draw the mean again, or excuse me, draw the distribution, the normal distribution, and think about areas. And we do the analysis that we've done, and we come up with the number. It will change. Instead of it being 1.96, it'll be something else. And so since that number is important, we give it a name. I think we alluded to this on last Thursday. It's called the critical value. So the critical value will change depending on which type of confidence level we would like to have. So what we do is we use the following symbol. So we know that this number 1.96 is connected to that Z table. And so what we do is we want to make sure everybody knows that, and then we have to give it a subscript. So we give it this subscript of Z sub alpha 2. So let's make sure you understand that. This reads Z sub alpha over 2. So now what we want to say is we don't just care about 95%. We want to come up with a systematic way of choosing any percent that our heart desires. 90%, 97%, 84%. And so this gives us a very systematic way of denoting things. So we're going to draw a picture in a second. So Z sub alpha over 2 is called the critical value. So why alpha over 2? Well, that is to tell us that when we take our curve like we had on the previous page and we look at the area under it, we know that there's this symmetry. And we know that there's these tails. You have your left and right tail, and the area under those tails is the same. So really you can think about being cut in half. So that's why we write alpha over 2. So let's list 3 standard ones. So what are 3 standard critical values? Well, the first one is what we did, but let's put them in order. So 90% is Z sub alpha over 2, and that's equal to 1.65. 95% is Z sub alpha over 2, which we already saw, 1.96. And then for the 99% confidence, Z sub alpha over 2 is equal to 2.58. So these numbers come directly from your Z table. So we always remember that the Z table is a list of those areas. Does anybody have a question or a comment? Going once. Going twice. Sold. right, so a good exercise to help sort of build your understanding of what's happening here, at least this idea of area and percentage of area, is to draw the picture and then use a Z table to sort of understand where these numbers are coming from. But it's sort of the reverse problem. Now you're saying, okay, what value will give me a Z score of blah? But then you have to sort of do the math, because depending on what table you're using, that Z table or that calculator gives you a different area. So if you look at our picture here, you have to be able to understand that the mu that corresponds to, say, this particular scenario, excuse me, not the mu, the alpha, here we're looking for 95%. That means what's left in the tails on each side is 0.002. So your job is to figure out which number right here will give us that 0.95 inside. So, what I would encourage you to do is play with that, investigate, get your hands dirty, as we say, and once you do that, you'll have I think you'll have a better understanding of it. Okay, does anybody have a question before we do an example? So let's make two other comments. So the first thing to understand is the above sort of interval analysis. If you look at the formula, it assumes we have knowledge of sigma. So a question you might have is, what if we don't? And then the other remark that you might, if you spend some time thinking about this sort of question or ask yourself, is how large should n be? So another way of stating that is, how do you know your sample's large enough? Do you, again, we talked about this before, but do you think we're going to get accurate sort of information about all 20-year-olds in their height if we just go out and measure 10 20-year-olds? I don't know. So these are questions that we need to ask. They're questions that unless if we don't ask them, then we're not really doing our job of analyzing the data or doing statistics properly. You know, an obvious question, I suggested this yesterday. Oh my God, here we go again. I suggested it last week. An obvious question that you might ask and should stir your imagination is, well, how can I know what sigma is but not know what mu is? And that's a good question. And that's why we study statistics in much more depth than we're doing here. But that is a good question. Now, of course, I can argue and say, well, maybe we had a previous study that suggests the standard deviation is blah. And you say, okay, that's fine. But then you could come right back at me and say, well, what did it say about the mean? Nonetheless, if we assume that we know something about sigma, then what we talked about will give us a good analysis. Or at least it gives us good information. What we make of the information is up to us. Well, if we assume that our margin of error, well, let's answer this let's answer them in order, I guess. So when mu is not known, one option is to use what's called the t distribution, which we will not discuss, but if you are interested, maybe you ask that question to yourself, now you know. And then to determine the appropriate sample size, how large to choose, we use the margin of error formula. So let's let E equal our error. And we know that E is equal to this. So solving for n, we'll spare you the algebra. If you solve that, you get that the appropriate size you should choose is z sub alpha over 2 times sigma over E quantity squared. So you say, I want this margin of error, and you plug it into this formula, and it tells you how large n has to be. Now, an interesting thing about this is think about your basic number sense. If you want a very small margin of error, and this is why, you might say this is all you're just writing letters down. And you could argue that, but if you think of this from an intuitive standpoint, what you know about numbers, basic arithmetic, this formula should make sense. Because imagine you want a really small margin of error. You want E to be small. Well, if e is small, that's going to make that whole thing inside the parentheses large. I mean, go to a calculator and take a number, take 5 and divide it by 3. Well, then take 5 and divide it by 300, and then take 5 and divide it by 3,000. So when e gets to be a very small number, say less than 1, it's going to make the whole fraction large. So the smaller e gets, the bigger n has to be. So again, that's, you know, I'd like to call that number sense. If I have a fraction, which I have on the right-hand side, I know that the smaller the denominator is, the larger the fraction becomes. Does anybody have a question about this? Okay, so let's do some examples before we call it a day. Does that show no one has a question? Let's see if anybody new has joined us now. There are still 4 of you, 4 legends who we do not know where everybody else is. There's breath. Someone's alive. Oh, someone's typing. Mine too, Liam. Mine too. No. Hey, you know what? This semester, are you done yet? Or how many more things are you guys having finals right now? Or what's everybody really doing? Like, are you taking finals in classes? How's this working? I didn't really even ask what other people are doing.
You're really the last class I have, technically.
Oh, so I'm the pain in your ass now, huh?
You could call it that, I guess.
All right.
I still have like 2 exams.
Well, that's interesting. Yeah, I don't envy what you guys are going through right now. It doesn't seem fun. It seems very confusing, and who knows? But I don't know. I would imagine everybody's going to be grading easy. I guess.
So how long is the exam going to be?
I don't know. I mean, for me, 10 minutes, but I'm writing it. You know, I don't know. It's a unique test. It's different. There's some questions on it. Well, you'll see. I don't know. I mean, I'm giving you a week to do it. I'm not saying it's going to take you a week by any means. And I hope I mean, if you want to spend a week on it, because whatever, that's fine. But I don't, you know, I anticipate that if you've done the last couple homeworks, the test shouldn't take you that long. But there's a couple writing portions to it that you might want to spend some time on for whatever reason. Yeah, I don't think you'll find it terribly difficult. Now, you guys, you know, Kevin, you've actually had a class or 2 with me before, right? So there's gonna be a problem or 2 on here that is challenging, but that's not to punish or make your grades suffer. It's to see if anybody wants to try to sort of figure out a more complicated problem that's not necessarily just like a textbook problem.
Oh, okay.
So there might be, you know, I typically write my exams that you don't have to get every problem correct to get a good grade. So, you know, if you're unable to solve a problem or 2, that doesn't mean you're getting a D, right? It's just, and depending on how it goes, you know, there's usually some sort of curve involved. So, you know, I tell you guys this every semester. I would not stress about this test in the sense that if you get it and you struggle with some, but you got a couple and you're confident about a few of them, that's great. And you do not hesitate to ask me any questions you have. I mean, I'd be happy to help you through email or a Zoom meeting. So it's not that you can't get help. The only rule that there will be is not to talk to each other about it. But that's, you know,
Right.
That'll be, you know. Okay, so Does that make sense? I don't know. Maybe it does. Maybe it does.
It does.
All right, so let's do an example. So let's do something fun. Okay, so here's something that you might get like on the exam. All right, so what's happening here? We got an email coming in. Pardon me a second. We will. Okay, so here we go. So a store is interested in how many customers it averages per day. Now, so how could a store go about answering this? Well, first off, we're being generic right now. What does it mean? How many customers per day? Does that mean how many people walk in the store? Does that mean how many people walk in and buy something? You know, there's lots of different ways of doing this, so we have to be a little more specific about what we're doing. We also understand that there's all kinds of, you know, subtleties to a question like this, but we're doing a very what we call generic example. So it's, here we go. So it takes 50 random days and finds X bar to be equal to 132 customers per day. So that means it takes 50 days, and it says, okay, let's have, how many customers do we have day 1, day 2, day 3, all the way up to day 50. Adds them up, divides by 50, and it gets 132 customers. I guess that's kind of silly. How about 132.3? Because there's nothing that assumes it's going to be a whole number if it's an average. Okay, now, from a previous study, if I can only spell on this thing. So from a previous study, it estimates sigma is 8.4. So what we'd like to do is we would like to do the following. We would like to determine the 99% confidence interval of the population mean. All right, so this is a typical textbook type problem. We want to know information. We take a random sample. Here we use 50. We have a sample mean, which is X bar. We have what we think is the true standard deviation. We're using a previous study. And what we want to know is we want to know that we want to determine the 99% confidence interval. So basically we're asking is what is the true mean? Where does it live, and how, where can we be 99% confident the actual mean lives? All right, so let's think about how we solve this problem. We solve this problem using the confidence interval. Now, if we go back a few pages, I told you, the standard number. So we know that we're going to use this 99% version. So the key number here, the critical value, is 2.58. Excuse me. So if we trust that what I told you before is correct, we can now write up a solution to this problem. So what is our solution? Well, our solution is it's X bar minus Z sub alpha over 2, and then it's sigma over root n, and then the true mean is mu. That's the guy we're trying to find, at least be confidence-wise. So now all we have to do is plug everything in. Now, remember, we're interested in 95 or 99%. So what is our X bar? Our X bar is 132.3. This is 2.58. Sigma is 8.4 over root 50. And then we have the same creature over here. Maybe I'll put parentheses here to be more clear with my arithmetic. And really now this just comes down to a calculator. So you either pull your one out of your pocket, or you go on the internet and grab a free one, and you just do the calculation, making sure to do your order of operations like a good little machine. All right, so so if I did this correctly, I get 129.235. And then if I now do the adding part, I get 135.365. So how do we interpret this? What do we make of this sort of little arithmetic? with all these scary symbols. So we can say with 99% confidence that the population mean, the actual mean, is between those two numbers. Does anybody have a question about this? Comment, concern? Going once, going twice. Comments, concerns?
What do you think about the state reopening?
Oh, dude, that's a tough question. I think that all these people making decisions are kind of in a tough place, because no matter what they do, someone's going to disagree, right? And I'm not even talking about whether they make the correct decision or the incorrect decision. It's just they make a decision. So it's people, you know, what's the standard phrase? You're damned if you do, you're damned if you don't. If you want my opinion, you know, my opinion is that things, I think it was smart to do what we did, as far as sort of asking people to stay home. And we'll probably never know if that is, so here's the issue for me. Is the virus, did it not spread as some people thought it might, because it's really not that bad? Or did it not spread like some people thought it might, because what do they call it? Social distanced, right? Yeah. So we don't quite know. And people who agree with the social distancing would say that that's why it is what it is. Other people will say it, you got your one group of people who call it all a hoax and it's all fear mongering, and everybody has their opinion. I guess we'll probably never know the true thing. But if you open up too soon and then things get bad, then I guess that gives you a hint to what's really happening. Yeah, I don't know. I'm kind of glad Pennsylvania's taking its time. We'll see what happens in like Georgia and other states. Let them,
I think it's going to be terrible.
Well, I don't know. I mean, again, it could be.
Could be, or
yeah. I mean, there's no doubt. I mean,
herd immunity might be a thing.
What's that?
Herd immunity, like
yeah, it could be. I mean, it's interesting too, because if you look at data, and this was a great, too bad we're not in a classroom and we can't like pull data up and do all kinds of stuff. Yeah. But if you look at data, how other countries have sort of tried to fight it, it's very interesting. There's so many things though. You can't. You don't know if something's a cause or if it's correlated. I know we didn't really talk about that particular stuff in this class, but causation and correlation is a very important thing. Did some countries do better than others, and why? And sometimes I think what's lost in a lot of these analyses that people give and they throw numbers out are all the subtleties. Like, you can't compare how Pittsburgh fares to New York City. New York City is a densely populated place where people use public transportation and interact with tons and tons of people all the time, where that just doesn't happen in Pittsburgh, right? Nor if you're the governor of Pennsylvania, you're Tom Wolf, thinking, you can't compare Pittsburgh to Philadelphia as far as how dense the population is and what day-to-day life is for most people. Where do they shop? How do they get from places? nor should you compare a place in like middle of Nebraska or Kansas to Pittsburgh.
Yeah.
So yeah, I don't know. I'm not an expert at any of this stuff. But there's a lot of people who are, and so I think the math nerds tend to think it's much more serious than some people want to. The big issue is here with what you suggested too, Kevin, is the risk.
Yeah.
There is, maybe it's small, but if that small thing does happen, very, very bad things happen, right? So, one of the phrases for that is what people call tail risk. Like, even though the probability of something horrible is low, it is still probable, or it's still possible, not probable. So, yeah. But you never know. But then there's also, a lot of people who say that it could come back in 4 or 5 months, even worse. Well, we don't know that, but it could.
Yeah.
Yeah. So there's a lot of ifs and whats and unknowns. I mean, it's quite interesting. I think my personal opinion is, and again, I don't know. I'm not an infectious disease modeler. I mean, I can do the math portion of it, but the math stuff, the modeling is only as good as the data we have, right?
Yeah.
So, and you obviously you can compare the data here and try to get information on what could happen by looking at past similar events. But, yeah, I don't know. We're going to find out because I have a good feeling that Pennsylvania is going to reopen on Monday next week. That's just I think it's been 3 days in a row now in Western PA. There's been no deaths. I could be wrong, or at least in Allegheny County.
Yeah.
So I have a feeling we open next week, whatever that means. But don't forget too, I think too, even if people do reopen, certain things aren't. Like, you're not going to have restaurants and places where people congregate in close quarters. So even if you do reopen, it's almost like you're still going to be social distancing, right?
Yeah.
And you have to wear masks everywhere.
I mean, everyone taking summer classes won't be at this campus.
Well, right, but no campus is having summer classes. I don't think I don't know of any universities that are having summer classes in person. Everything's online.
Yeah.
And I would imagine that every university has 400 plans for what's going to happen this fall. As far as, are we full face-to-face, or are they going to limit classes? Are they going to, I mean, think about a dorm. A dorm is just like a perfect laboratory to study this kind of stuff, right? You have a bunch of people living in close quarters, and it's just, I mean, that's, if you look at some famous studies of like flus and disease spreads, a lot of them, a lot of those famous studies come from like boarding schools and, college dormitories. It's a fascinating thing. I don't know the answer. Part of me wants everything to get back to normal, but part of me also doesn't want to go too quickly and then have a setback.
Yeah.
It's and I see a lot of sides of it, because you feel for why can some businesses be open and others can't.
Mm-hmm.
Like, I like beer, but I find it funny that the beer distributors operate, and their argument is, well, they sell potato chips and like pretzels, so they're essential. But then other small businesses aren't allowed to operate for whatever reason. So I think that's, there's not a correct answer that solves it for everybody either. So that's the other problem. Mm-hmm. If one group of people are benefit from certain sort of policies, it's going to undoubtedly be negative for another group of people. And so that's why you get this sort of, you have these Looney Tunes out there with machine guns, and everybody's taking their voice and complaining either way.
Yeah.
Yeah, it's funny. We were at the park yesterday, me and Amy and my girls, and they're like riding their bikes. We like to go up to the park. That way they don't have to worry about cars and stuff. And so
Yeah.
my mother-in-law's there too. So we're just like in this big parking lot. The girls are riding bikes and scooters, and there's people walking and running. But this old lady, when she comes into the parking lot we're in, she like covers her mouth as she walks, like it's like a cul-de-sac. And it was just so funny. Like I was thinking, now is she afraid of us or is she protecting us? Does that make sense? Like she was nowhere near us. Like she was not ever within like 30 feet of us. Like she walked in the parking lot. There's like a little turnaround in the end of the parking lot. But she was never near us, like with anywhere near like 10, 20 feet of us. But she put her shirt up like this. And I thought to myself, I said, is she afraid to breathe our air or is she protecting us from her air? I just, part of me laughed. Part of me was like, is she okay? It's one of these strange things.
I know.
And then I saw these people bitching, part of my language, they were bitching about joggers. I guess it's different in like New York City, right?
Yeah.
I mean, I don't know. I mean, I live by White Oak Park, which is an Allegheny County park, and it usually gets fairly crowded this time of year. There's all these graduation parties, and there's a bunch, kids in the playgrounds and all that. But now it's even more crowded because people want to get out, I think, because of social distancing. They take walks and get outside. But so I've never seen anybody like running with a mask. I've seen a few people walking with a mask.
Yeah.
But I guess this one guy was complaining that in New York, him and his buddy, one's in New York, the other's in DC, they're flabbergasted that people aren't running with masks. So they hate runners because they said part of me says they're probably right, but part of me is like, I can never run with a mask.
It's uncomfortable. It's
well, I get annoyed, not because you want me to wear a mask, I'll wear a mask. I'm not going to fight it, but it makes me sneeze. So like the first couple times I went into the grocery store, I would literally, I'd go in there and I'd start sneezing right away. So people probably thought I was like running around with a Roni. So now what I do is in my car, I put it on and I like rub it into my face to get all the itchiness gone. Then I sneeze a few times, then I go in. So
yeah,
it is what it is. I don't know. I don't even know how much. Well, I'm not going to get into that stuff. But, these are strange times. One thing's for sure, when this is all over and done with, hopefully sooner than later, we're going to look back, and then years from now, you're going to be like, man, remember that stupid coronavirus of 2020? I just, pain in the what.
Yeah.
And it's weird because like I'm in a different, everybody's in a different situation, right? I mean,
yeah.
I live in like a quiet neighborhood. There's not much traffic on my road. I'm not like in a densely populated place. So I don't even interact with that many people. I always think about like the differences, like say you lived in like an apartment complex or, if you lived in parts of New York City where like you'd probably encounter thousands of people a day that you don't know. And you've touched the same buttons on the elevator as thousands of other people. And think about how quickly those connections multiply of how many people you interact with either directly or indirectly. So it's just so wild to me, like, how different this thing could be depending on where you live. So, yeah, I don't know. It's interesting times, is it not?
Very interesting time.
Yeah. You just got to be safe. I don't know. Sometimes you got to do things you don't want to do. Like I hate wearing a mask, but I have to. So yeah. I went golfing on Sunday, so that was fun.
Oh, with a mask?
No, I didn't wear no damn mask. But I found it funny. We laughed. I'm recording this. I'm going to stop recording this. No one wants to hear this.